I was watching some videos about Raylib on YouTube, especially about how to compile C and C++ games made with Raylib for the web using mscripten. One of the best videos I found was from my fellow YouTuber, Programming with Nick. The process is relatively straightforward, but it is a bit more complex than what I'm used to with Python and Pygame. Anyway, after watching the video, I got curious about other Raylib related videos on his channel and came across C++ Raylib vs Python Pygame speed comparison in the Game of Life simulation. I was intrigued by the comparison since I had done similar ones in my last video, but in my case using Raylib on Python, not on C++. And Raylib showed clear advantage, especially with many high-resolution sprites or 3D graphics, which are beyond Pygame's current capabilities due to its lack of hardware acceleration support. So when the results came out, Raylib and C++ performing almost 10 times faster, it wasn't really a surprise. Still, I wasn't fully satisfied with the comparison. After years using Python and Pygame and a few weeks with Raylib in Python, I felt the test didn't fully explore Python and Pygame's potential. So I decided to optimize the Python version myself to see how far it could go. I don't have a C++ version here, but running the original Python version with Pygame gives me around 25 FPS, slightly below Nick's 35 FPS. Probably because he used a desktop with a better CPU than the one on my Steam Deck. Extrapolating, Raylib in C++ should then reach about 250 FPS, assuming it is CPU bound. The first odd point in the original video is that it compared Raylib in C++ to Pygame in Python, even though we also have Raylib bindings for Python. So I rewrote the simulation in Python using Raylib instead of Pygame to make things more even. With those changes, I got about 22 to 23 FPS. Wait, it's worse? Exactly, I have seen this before. Sometimes Pygame is faster, especially when rendering simple geometric shapes, but I suspected the real bottleneck was in the simulation itself. It iterates over more than 15,000 cells to decide which ones live or die in the next step. Anyone with Python experience knows that this kind of operation is a weak point and should be avoided whenever possible. The solution is often vectorization, performing operations on entire arrays at once instead of going one by one. That's where Numpy comes in. It implements critical functions in pure C for maximum speed. Here I just needed a 2D array to store the cell states and then sum each cell's neighbors using the roll function, which shifts arrays around before summing. After that, empty cells with 3 neighbors and live cells with 2 stay alive. The rest become empty in the next step of the simulation. With this improvement, it reached 30 to 34 FPS. I know, not the huge leap I was expecting. At this point, I stepped back into my comfort zone. Pygame. Pygame has the surf array module, which allows converting a Numpy array directly into a surface, avoiding iteration over every cell to draw rectangles. The surface is the same size as the array, but since each cell is larger than 1 pixel, it needs to be scaled up to the screen size before splitting. With that and the Numpy optimization, performance on Pygame jumped to an impressive 200 to 250 FPS. Now we are talking. That more or less matches the earlier theoretical estimate. But there is one small difference. The cells are touching. There is no 1 pixel gap between the cells like in the original version. To fix that, I created another surface just for the grid lines and blitted it on top. Now it looked identical, though the frame rate dropped slightly to around 180 to 215 FPS, still very respectable. Then I wondered, could I do something equivalent in Raylib in Python? After some discussions with ChatGPT and a few tests, I can say with confidence, yes, it is possible. In Python Raylib, we can use the FFI foreign function interface, which handles bindings to the C functions. One of these functions, cast, lets us create a C buffer from the Game of Life array. away. That buffer can then be used to update a Raylib texture. This texture is then rendered to the screen size using Draw Texture Pro. And as with Pygame, the grid lines are rendered on a separate texture and drawn afterward. Finally, after this, we reach a whopping 700 to 800 FPS, almost 3 times the optimized Pygame version and almost twice Nick's C++ version on his PC. Now I can rest easy knowing that the Game of Life has reached its true potential, both in Pygame and Raylib. Of course, there are probably more optimizations that could be done, but I believe we are already at the point of diminishing returns. I know, this is just a simple example and not very representative of real games. There's not even a player here, so it's a bit weird for me to call it a game. Python's big advantage in game development and programming in general is accessibility. It's easy to learn, easy to get help, and great for testing ideas quickly. But when it comes to performance, as in life, the easiest path is rarely the best one. There are many tricks for better performance in Python. It depends on your problem, but vectorization and C++-based functions are key. There are also tools like Numpy, which perform just-in-time compilation, and Cython, which compiles Python functions into C, and there's also PyPy, but I didn't use it much yet. Often though, the issue is the algorithm itself. It takes experience and brain power to find the right approach. It's true that C and C++ and other compiled languages usually perform better. But Python is still a capable language, even though it's interpreted, largely because it relies on libraries and modules written in faster language for critical tasks. In any case, you should use whatever works best for you. As long as it doesn't get in the way, slowing your development, that's perfectly fine. The scripts used in this video are available on GitHub if you want to check them out. Hope you enjoyed the video. Until the next time.